All right, so let's run through the different wave parameters, right? And the wave phenomena. Right. What are the four things that waves undergo? Tisha, what's up here now? Right? The four things that waves undergo are reflection, refraction, diffraction, and interference, right? So let's just run through the form for 5 stuff here. Laws of reflection, the incident ray, the reflected ray, and the normal at the point of incidence all lie on the same plane. The angle of incidence is equal to the angle. Is equal to the angle of reflection, right? Right, all that we know from form 5. Refraction, the first law, incident, refracted, and the normal, of course, all lie on the same plane. And then the second law is the angle, the ratio of the sine of the angle of incidence to the sine of the angle of reflection is constant. So we have Snell's law there, right? Sine theta 1 and sine theta 2 is constant, right? And that constant is called what? Severe. No, what here is called the constant. Refractive index, right? It's called the refractive index. Right? Refraction is a change in direction of travel of a wave at oblique incident passing from one medium to the other. Refraction is caused by a change in the speed of a wave, and there is also a change in wavelength, however frequency remains the same. Right? So what's the next formula for this here?
Equals F. Equals F.
No, so Snell's law here.
And one sign for one single.
Right, so you have that version as well. You have the version N1 sine theta 1 is equal to N2. And next one.
What about C is equal to
That's
That's typical angle. Right, remember we just said the speed changing as well, not just the angle. So basically speed in medium 1 over speed in medium 2. Right, or lambda in medium 1 over lambda in medium 2. All of these here could give you the refractive index. Right? But anybody remember how to write it? It's the refractive index of what? Let's see this happening. Let's say you have medium 1 here and medium 2 here. How you write it? How you write here? There's a way to write the refractive index instead of N.
1 and 2.
Right? In this case, it's the refractive index of 2 with respect to 1. Refractive index of 2.
Sentence 1. Not wrong.
Right? So what do we do? What do we refract in here? 2 or 1?
Sign of one.
But what do we refract in? 2. So the refractive index of 2 with respect to 1. Right? So if this medium change, then this will change, and of course, this will change, right?
So if we go from air to glass, cheat and
If you're going from air to glass, it will be fine. Right, and remember, frequency remains the same, right? Note that if there's an increase in the speed of a wave in the second medium, it refracts away from the normal, right? So if it slow down towards the normal, speed up away from the normal. All right, less dense to more dense is what? So what's away from the normal? Here we have a simple example showing how it works, right? Right, note that there's an increase in, yeah, let's go towards the normal. When I speed up, it goes away from the normal. Right? Diffraction is what? Diffraction is the spreading of a wave which is limited by the obstacle or gap. Larger the opening, smaller the diffraction, smaller the opening, the bit bigger the spreading, right? So diffraction is the result of the superposing of secondary waves from a coherent source on a continuous section of a wave front that has been limited by an obstacle or gap. I'll show you a diagram just now, right? Or a small simulation. The degree of diffraction depends on the relative sizes of the wavelength of the wave and the obstacle or gap. All right? So those are things I need to remember diffraction, right? And I don't know if you did it already, but there's something called a diffraction grating. And there's a relationship or formula to go with it. Remember that? Diffraction grating. And just split it a little light up. We will do that in a little while. Interference. When two waves meet at a point, the resultant is the vector sum of the individual displacements of the waves at that point. This phenomenon is called interference. Right? It's a result of the superposition of waves. And it has two types of interference, constructive and destructive, right? Constructive occurs if the waves are in what? In phase, and destructive occurs if the waves are out of phase. What are the three factors that control interference? We have that. That's what she. That's about that. Right. I'm not sure if you all can see it here, right? Actually, let's do about something fast. Let's say you have something like this here. Adam, tell me what happened here now. Let's say you have waves entering here, Adam, of a particular wavelength last now. So it will diffract through the openings, right? So it will diffract here. So what is happening there when the two diffracted waves come out? Sorry, when the waves come out from slit 1 and then slit 2, they'll undergo diffraction, right? But then after a while, what happens in the middle here? Interference, right? So what you will have being formed on a screen, you will have some kind of interference pattern. What does it look like? What the pattern does look like? So it might be bright, and then dark, and then bright, and then dark, and so on, right? Right. Well, what are the three things that affect the separation between fringes? Three things. Wavelength, number one. So wavelength affects it. What about this slit opening here? Will that affect it? The slit opening. Separation between the slits, I mean. Will that affect it? Yes. What about the distance from the screen? Yes. So those three things affect. Right? These three things affect why. How the fringes are separated, Nathan. Right, Nathan?
So size of the sun.
So size of this, sorry, separation of the slits, that's A.
Right.
The wavelength coming in, that's lambda. And the separation between the screen and the slits. Those three things affect Y. Right? And we'll look at the formula. Anybody knows the formula? Y is equal to what? MX? Who said that? MX plus C? Very good. Right? D lambda on A. Right? And we have to prove this formula. D lambda on A, right? So those are the three factors that Keshav. Asha, let's do. Asha, what's your name again? Next to Keshav.
Yeah.
What's your name again?
John.
Pay attention.
Say
Right? So those are the three things that would affect Y. Right? The further away T is, what will happen? Y will get bigger or smaller? Huh?
bigger.
Right? Y will get large. Y will get larger. The bigger the wavelength, what will happen?
Bigger.
The bigger the wavelength, the bigger Y will be, and the smaller A is the no, bigger Y will be. Here's this. I'll give you all this just now. We ain't not doing this today. That's good. So those are the three things that will affect it, right? Yeah, this is number. All right. So I want to go a little more into refraction.
So. So money, hold on.
Yeah, I mean,
So say a marginal. I beg my thing a margin.
that's not what.
I think that person.
No, that's correct. It's like, I mean, I'm not sure, get up.
I just went one.
That's correct. That's correct. I make a mistake first. All right, let's focus on refractive index now, right? All right, so what is here? Right, I made a mistake. Let's take a look at, you'll remember the three important things in refraction. And that refraction, of course, what's the next important thing that you need to remember? Critical angle and the third thing, total into.
So anything is changed from society.
Yeah,
Yeah.
we get a little more time.
Yes, please.
How much more? Not this refraction, but there's diffraction interference. That's what different. Right, so I made a little mistake here, so I want to fix it here. Write this down. Correct in the handout, right? Right. So watch here. So here we have the refractive index, right? I told you the wrong thing the first time. Let's flip it around. This medium 2 doing the refracting, and medium 1 is what with respect to. So here the refractive index of medium 2 with respect to 1. I said it wrong the first time. Don't forget that, right? Sorry about that. It's the refractive index of medium 2 with respect to medium 1. All right? So it's written like this. And the formula is sine theta 1 over sine theta 2, or the speed changing, right? Speed in medium 1 over speed in medium 2. What else changing? The wavelength. So wavelength in medium 1 over wavelength in medium 2. That's okay? Right. This version here could also be written like this. Right? What I want you to notice here is that you see nothing here. When nothing here, what do I assume? What do I assume here? When you're not seeing anything here. So you see like here, you see the refract. Nah, you see the refractive index of 2.
So yeah, assume is here.
You assume it's here. Right? So you assume it's here. So if I said the refractive index of glass is 1.5, you assume, right? You assume that's from A. That's okay? You assume it's from A, right? So nice. So you have this relationship here and you have this, right? Everything here is to do with refraction. If you go from, which is more dense, Adam? Adam? Which side is more dense here? Medium 1 or medium 2? Medium 2 is more dense. Very good. So the density of 2 is greater than the density of 1. All right? Because it slowed down and it went towards the normal.
Right, I think before it's like when does move away and up. So when does move away and up, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will be like this. So when it moves away, then it will
It's in the handout.
Alright.
So instead of peeping in class, what you could do is write it down. Right? Right, next time I'm not gonna talk about it, but I just kind of leave the lesson, right? I don't want the people inside the classroom, please. Everybody. You going? Right? So this here is this is a basic relationship here, practice index, right? From here now, we began to do a proof for this in a little while. But before we do that, let's just go over the form 5 stuff. What has happened if R is 90? If R is 90, right? If R is 90, let's say we have something like this. Let's say we have air and glass. And the normal is here. Right? Let's say you have an angle of incidence here, right? That given you angular refraction of 90. And the ray will travel here. What do we call that angle of incidence? Critical angle. Right? Which could be used. Right? In this case, I use R. But the same thing, C is critical. All right? So your critical angle is this. How you find critical angle?
Sine C equals 1.
Sine C.
So sine.
All right, right. Sine inverse 1 on. All right. Sine inverse 1 on the refractive index. The critical angle, that's this angle of incidence, that gives the angular refraction of 90. Right? So here, the angular refraction is 90, then I is your critical angle. Right? But what would happen in this scenario? If the angle of incidence is more than the critical angle. So if I is more than C and the ray stays in glass. And the ray stays in the glass. What happened? Total internal reflection. The ray not coming out here again. It will be right, then total internal reflection occurs.
I is more than C, all stay in glass.
Huh?
I is more than C, all stay in glass.
If ray stays in, well, I mean generally then some medium. Right? Then some medium. So if the ray is denser medium. And it undergoes total internal reflection. Air, glass. Yes, I and that will be equal, right? I is equal to R. These two conditions must be met, right? If the ray is denser medium and this happens. Right? Copy it down. I want to do a little proof there for you. This one never come before. It never know. They can ask you. I never saw this one. This come long time. It's 19.
So you can do a freaking if you us.
It's just me on.
So you do not apply the
I see all that. I can't do that. I can't do a
Yeah. Let's just be like. Yeah.
So Adam, since it's in our writing, right? You can tell me what this is? What this is here? What is 2,1n? Look at what you have there. Like you have 1n, look what you have here.
So just be
It will be the opposite, right? So it will be the refractive index of 1 with respect to 2. Right? See if we can get a relationship from now. A quick little formula there. Oh yeah. Number one time.
Every problem.
Right, sorry. So here was asking, right? I was asking for a relationship V2 and V1, right? So if it's V2 and V1, in terms of this, what will it be? No, but then I'll write back this. What I'm asking is in terms of this, what is 2 and 1? And 2 1 and 1 close.
And one and two.
And one side, see that.
No, hold on. Just in terms of that. So what you all recognize? You all just told me that 2 and 1 is V2 and VP1. And but and 1, 2 is V1 and V2. So my question is, how do I write 2 1 with respect to 1 2?
Yeah, making sense.
How's the write that?
And one and two.
Huh?
And one and two.
No.
Two and
But you're close.
So, what?
So,
So,
But just somebody just say it in about time how it was going.
so.
No, not just for sure. Kind of, what you say? What you say? Kind of. No, somebody want me. And you know, Joshua. Kind of. What you say? Something you was suggest. Anyway, so basically, and you'll flip it over, kind of. And you'll flip it over.
Yeah.
So are these two related? Yeah. 1 over this. Right? So the refractive index of 1 with respect to 2 is the same as 1 over the refractive index of 2 with respect to 1. All right? So I'll try to get that. Right.
well, you didn't see it.
Huh?
You didn't see it.
Well, I wanted this in terms of nothing else.
This.
Now, what I'm
Yeah,
saying
like
is
a one can list.
in terms of right. Also, let's say we have something like this, right? Some of what you all think this will be. So if I said the refractive index of A with respect to medium 1 multiply by the refractive index of medium 2 with respect to A. What would this be? 1. No, that's 1. What would this be? 1. The refractive index of, what will it be? 1 then 2, yes. Right? So let's break this down. Right? If I break this down, what will this be? And this will be sine, let's use speed. Speed will be easier for them. This is speed in air over speed in 1 multiplied by what's here?
Speed into
Over speed in. What will happen here with the speed in air? So you're getting V21, which is what?
F2
Which is?
F2
Which is the refractive index of? Come out to write it. I want you to get in the habit of telling me writing it like this. Refractive index of what?
medium to with respect to medium.
So it's going from medium 2 to medium 1. So the refractive index of
2 to 1.
1 with respect to, right? Am I correct?
Yeah.
So it's going from medium 2 to medium 1. Medium 1 doing the refracted with respect to medium. Right? There's some small things to remember. So from this now, we can kind of jump into a small question. That was
So you can do that.
one by just over.
Yeah. See, it's not so easy. Just now, yeah, I was trying to get back this piece. That's not my thing. Think about this question. Anybody have 2019? Paper 1, paper 2? Check out see but to be able to understand it. So like on this side we have 1 and 2 harness. You want on that side is now 1 and ER.
Say again.
Right, so on this side you have 1 and 2.
Yeah.
You have the 1 and 2, right? By now it's now the 1 and 3. Sorry, 1 and E. 1 and E. I didn't realize that I said
1 and 8.
right, how come it's not the 1 on E? Yes.
Yeah, so I think that's not. Yeah, and they were 2019. The sun come out. You get? Okay, yeah. Let's take a look at 2019 and that one there now. Check in the group. Let's shift. I'm gonna share back here.
Actually, our last point.
You all see that? Check in the group. We're doing it number 2. I will share on board as well as the master. Now, then the whole thing of going down to the end there. Yeah, thanks. Yeah, page 16. No, we're not doing the length. I'm sure you that's the page, pattern. That's in here. Pattern. Right? What's the refractive index? Look at showing you there. Right? So let's start from here now. Part 1 is just a definition, right? It's on page 16 on the passage book. All right, let me take a look at this now. Right, so a ray hits a glass prism. It's a triangular glass prism. Look at the ray. The ray entering at what angle there, Adam? It's on page 16, Adam. I think you're looking for it. Page 16. Look at the ray there. Where I recognize tunnel. So it's traveling along the normal. You're traveling along the normal. Now something else. When a ray travels along the normal, what is something? Undeviated. Right? So it will travel along the normal undeviated until it reaches the surface here. Oh. Right, I need some help. What's the angle of incidence there? A little bit of maths. No, maybe some what they give you.
90 months.
Right, it was like.
So by tomorrow.
I mean, based on that.
Oh. Oh, for
Right, so what's here? What's the angle here? Daniel, what's the angle there? Right, 45. Right here is 90. Well, they told us theta is 45. So here is 45, here is 45, and here is also 45. Sana, you okay with that? Right, determine by calculation whether the ray will pass through PR. So what they asking for, Keshav? What they asking for? Will the ray pass through PR? Yeah, what they asking for then? What they asking you to find? Critical angle, right? Because they want to see if total internal reflection will happen, right? So they actually ask me to find the critical angle, so you'll determine if the total internal reflection will happen. Hurry up, use the formula. Use the formula for C. I'll just go through that, read it. Yeah.
Side just one I get one voice up.
Hmm?
41.
41.14. Right, so the formula is what? So it will be sine inverse 1 on n. So that's sine inverse 1 over 1.52, which is, what else? 41.18, right? So 41.2, 18. Yeah, it's actually sine of already.
You don't sign up, for example, like a unit 2 years old.
I think I will want. Yeah, if that if
If there's a way about you can.
you do bad and you have that so that's it. It's 75%.
Yeah, sorry. Nah, it's 79. This school is up.
One thing is going to be saying, they're not.
I study I in classes, also my 4 classes.
So what
Just from since we started in half 6, she never gave me a house.
whenever I'm like that, I want to work. Canada, I was like 3 main things that like come on, I know what to do cable pump example, but you have to know when you have you have to to help you recognize it, I don't understand the fraction, I don't understand the answer. So you can spend more time in crash course on those things. So what I want to do is I'll do free like something stupid and some. I want to bring all the evidence like, yeah, get more easy. Like you become a teaching fraction. I will correct the other go along. And then we can practice some more questions. No, I'll do a whole leave some for stuff like. That's why how much over the books are like, I have to do a one. But now on.
I don't feel I want to
We just need 1 to 3
yeah, what do you want to six
like I that was not going to happen. After the crash load, it's right, yeah, so what will happen? Critical angle is 41.1. No. Right, the angle of incidence is 45. So the angle of incidence is greater than the critical. They have to write the answer, right? Because they ask whether or not. So you have to say the angle of critical angle is 41.1. So number 1, tell them that the critical angle is 41.1. Therefore, the angle of incidence, which is 45, is greater than critical angle. And what else? Ashad, what's the next thing? No, you're missing one more thing. It's in the denser media, right? In denser media. Therefore, total internal reflection will happen and it will not pass through PR. Okay? It will not pass through PR. Yeah, so since most of it come on so just get my idea when on the exam or something. So we could pick up 2 days and run over each module and practice before you mock exam. I will to write it, especially for physics. Right? Make sure to write it. So this is 10, yes. This is the first thing now?
Yeah.
This is physics. Right, but the good thing with how exams is now and after class we still have another 3 4 exams. Right, and you have more time to keep practicing.
So, there's like 1 year after the other.
Huh?
You see it, so you give me something.
They have 3 in a row, I think.
Yeah.
So they have a break and then 3 in a row and then.
I will like how we exam. Whenever we talk about once,
This is very useful. Hopefully after we come play now session too. I don't know what the logic is saying. I guess oh you have to face out. Yeah, we're not talking on after.
1 week first, like average is like 1 exam, so first paper 2. I like 5 to
I
7.
think a big difference. I need to get a study from 2 on 2 and see.
I have come up since
What?
yeah, not come on phone, not something.
I don't buy somebody have 2 on 1 day. Somebody have 2. Right, next part. Sorry. Next part. On the diagram, draw the passage of the ray. On the diagram, draw the passage of the ray. What you gonna do? Now somebody use the wrong word there. Reflected, right? At the same angle of incidence, right?
So
Straight up.
So it will go all the way down.
Right.
So the wave bend to 90 degrees, right? What will happen at QR? Adam, like better like this. What happens at QR? It will go straight through, right? On the right, there's drawing the diagram now. But when you so strong outside, real strong. Next part. Without it? Oh no, that's the wrong question. Next one.
Sempre lançar como será? Cara, já ela vai. Ela faz
Yes, no. I check that.
But let's take a minute. My past papers, I am not seeing. Alright. I will look for that time you do that question next. We have a next question on just like this or a critical answer, but let's see the Alright, so the last thing I want to look at today before we go into before we go into diffraction. Right, so if you look here, right, you might remember this on form 5, right? If you have to find the refraction to a glass block, that's a mistake, and that should be refraction. Right, Keshav? But what you do is you put your 2 pins here, go to the opposite side of the normal and see if all the pins line up, right? And right, but what you call this gray again, this is emergent ray, right? But what we know about the angle of incidence and the angle of emergence? Keshav, what you remember about the angle of incidence and the angle of emergence? This angle here and this angle here, they are always what?
See.
The same.
Part of
Right? So the angle of incidence is almost the same as the angle of emergence, right? So these two rays here, incident and emergent, are parallel. All right. Here we have an example of the deviation that a ray will undergo. If you look at the ray, it undergo refraction, refraction. This entire thing here, we call it the deviation. You all remember how to show the deviation here? How you show the deviation of the incident ray? Think about it, right? If that glass block wasn't there, and the ray would have traveled like this.
Yeah.
Yeah, the ray would have gone in a straight line, right?
Yeah.
So the deviation is this here, right? The deviation and the separation between the incident and the emergent, right? That's how much it deviates. Okay? Right? And here, well, here's the example of
deviation as well. Right, we talk about total internal reflection and we talk about critical angle. Right here we have an application of total internal reflection. So for example, in fiber optics, Keshav, in fiber optics, right? Do you want the rays to come out? No. You want the light rays to stay inside. So the only way you can achieve that, because this is not a straight line, the only way you can achieve it is by allowing it to undergo total internal reflection constantly. Right? So it stays trapped inside the fiber optics.
Or we could also figure out from the.
I mean,
So uncle does it today.
no, it will still undergo total. Angle what? Angle this? No, you can bend this however you want. Right? It's not going to. Well, of course, once it bend, it have a space for it to flow out, right? So you can't bend it too much and the ray can't.
If the cable is so straight,
Well,
no.
if it's straight, we're going to feel that. No, but inside, although you see in the cables running straight inside, it's like that. Inside is a very much is a what is called the cable, what is called the wire again. Inside is a little wire that wound like this. Can't mind the name. The fiber optic cable is not the black part you see on the outside, a little piece inside. Right? That is a bend like this. Right? And the reason for that is that the core has a high refractive index. Right? Higher than the flat.
So technically, right? One area could come up.
Who's that? Oh, just, yeah.
Technically,
Technically, I recall.
but it says like. What was your part of next example?
I don't know the material, but the refractive index is always smaller.
Oh, you know.
That could make it.
No, wait, go.
Then it wouldn't make it at all.
No, okay.
The way it's designed is designed for the rays to never come out. Otherwise, you won't receive a signal.
Where's some side? Something.
But if it bursts or something, well, yeah, but then they'll have it one circle probably. Yeah, if it ever kink and it causes something get, then they'll have to fix it. That's why those materials, the material that they use is to reduce that. They don't naturally have those kinks. Because you don't want to be watching wherever and you have a kink and it carries a signal, right? So it's designed for that not to happen.
Sure.
Right? And what's the advantage? You carry more information, more secure, thinner, and lighter. Cheap. Well, now it's cheaper. It wasn't cheaper before. Right? Now it's cheaper. All right. The next thing we have to look at is interference of light and thing, but that's a long proof. Right? So I'm not going to do that proof today. But I want to just go over this here. Right? If you look at this interference here, you'll see the interference pattern. You see the pattern here, Keshav?
Yeah.
Bright and then dark and bright and then dark and so on. Right. What were the three things that we said, Keshav? Between you and Asha, I want to look at that. Right? What were the three factors that control the separation here? The to the what? Right? To the light source or the switch. Well, technically, our sources was here in the example I gave you, right? Right? The split separation and one more thing. One more thing. Lambda. The wavelength coming in. Right? Those are the three things that have affected this pattern here. All right? So what we're going to do next week is we're going to create a formula for Y and use it. All right. That will work out. Right? Right? But if it's a frequency, then you have the speed and thing as well. So yes, lambda is good. Right? All right. So I won't do that proof, right? Just to give you an idea of what left. We have to do this proof here, interference, something called diffraction creating, and lenses. Right? Those are the three things left in module 2. Module 2 is supposed to be the harder module, so I want to start the revision after with module 2. Right? You want to go over these things and do more questions on it. Right? May not get to do it on Saturday unless all want to take a longer break after pure.
Then we do a longer Saturday session, or if you're not in school, Tuesday or Thursday, we can see you man. Or like, come here or whatever we do. Right? I will let you know, right? But let's finish up this first.
I'm talking all day, physics.
Huh?
All this good physics.
You saw that. I can't put it any other day. People have the lesson something other day. Alright, so we'll stop there for today.
Okay. Good.